This is section 3.6, Zeros of Polynomial Functions, day 2. So we're starting out with the fundamental theorem of algebra, which says if f of x is a polynomial of degree n greater than 0, then f of x has at least one complex 0. We can use this theorem to argue that if f of x is a polynomial of degree n greater than 0, and a is a non-zero real number, then f of x has exactly n linear factors. So in English, for any polynomial of f of x with degree n, there are exactly n zeros of f of x. So let's find the zeros of this function. So remember, we're using our rational root theorem. We say that p is the factors of our constant term, so it could be plus or minus 1 or 3. Q is our factors of our leading coefficient, which again could be 1 or 3. So p over q, we could get factors of 1, 3, or 1/3. So I'm going to set up synthetic division. So 3, 9, 1, and 3 are my coefficients. And I'm going to try out negative 3. So bring down the 3, negative 9, 0, 0, 0, 1, negative 3, and 0. So that works. So negative 3 is a factor. And then this leaves us with 3x squared plus 1. Well, let's solve that. Set it equal to 0 and solve to find our other factors. So subtract 1, 3x squared equals negative 1, divided by 3, x squared equals negative 1/3. So x equals plus or minus the square root of 1/3. Remember, actually it's negative 1/3. Remember, we can't have a negative in a square root. So it becomes plus or minus I square roots of 1/3. So our factors, or our zeros, are negative 3, I square root of 1/3, and negative I times the square root of 1/3. Using the fundamental theorem, we say that our degree is 3, so we should have 3 zeros. Our complex conjugate theorem says that if a plus bi is a factor of f of x, then a minus bi is also a factor. So if you have a complex number, its conjugate is also a factor. So let's find a fourth degree polynomial with real coefficients that has zeros of negative 3, 2, and I, such that f of negative 2 is equal to 100. So we want to think, okay, our zeros are negative 3, 2, and I. It's a fourth degree polynomial, so we need another 0. Using that complex conjugate theorem, we can also say that negative I is also a 0. And then we say, okay, where did these come from? Well, negative 3 comes from the factor x plus 3. 2 comes from x minus 2. I comes from x minus I. And negative I comes from x plus I. So those are our factors. We have some leading coefficient out here in the front, a. And that's our function. Now we need to find an a that works such that f of negative 2 is equal to 100. We've done this with quadratics before, so I'm going to say 100 is equal to a times negative 2 plus 3 times negative 2 minus 2 times negative 2 minus I times negative 2 plus I. So 100 is equal to a times negative 4, because remember this is going to be 1, this is negative 4, and then I'm going to FOIL out these last two to get 4 minus I squared. Remember, I squared is the same thing as negative 1, so this whole piece here becomes positive 5. So 100 equals negative 20a. Divide by negative 20 on both sides. So negative 5 is equal to a. So what we can do is we can go back to our original, erase a, and put in negative 5. Then we have our polynomial. Last thing to talk about is Descartes' rule of signs. So for a polynomial f of x, the number of positive real zeros is either equal to the number of sign changes of f of x or less than that by an even integer. And the number of negative real zeros is either equal to the number of sign changes of f of negative x or less than that by an even number. So what that looks like, if we're going to use Descartes' rule of signs on this one, so here's f of x. What I want to do is I want to count how many times the sign changes. So a negative to a negative doesn't work. A negative to a positive works. A positive to a negative works. And a negative to a negative doesn't work. So for our positive real zeros, we have 2 sign changes, or the rule says we can go down by an even integer, so basically subtract 2, or 0. So this function could have either 2 or 0 positive real zeros. To do the negative ones, we take f of negative x. A negative number to the 4th power isn't going to change, so it's going to be positive, so this just stays negative x to the 4th. Those odd exponents, those are going to change signs, so plus 3x cubed plus 6x squared stays the same, and then minus 4x becomes a plus 4x, and then minus 12. Then we go ahead and count our sign changes again, so we have 1 here, so that works. This one doesn't. This one doesn't, and this one does. So for negative zeros, we could have 2 of them, or we could have 0. So remember, this Descartes' rule of signs is talking about real zeros. So notice, for example, we don't know this, but what if it had 0 positive and 2 negative? Okay. If it had 0 positive and 2 negative, the fundamental theorem of algebra tells us that if the degree is 4, we have 4 total zeros. So we have 2 right here, real ones. That means we would have to have 2 imaginary, because the sum of all of these should equal the degree.